Jupiter killed a planet 4 billion years ago, and it hasn't stopped throwing the pieces at Mars since. That's not a metaphor. Between Mars and Jupiter sits a ring of rocky debris, millions of chunks of rock and metal that were supposed to become a planet, but never did, because Jupiter's gravity was too strong and kept tearing the forming world apart before it could grow. The pieces are still there. Jupiter is still pushing them, and Mars is the first thing in their way. Most people picture Mars colonization as a Mars problem: wrong atmosphere, wrong temperature, too far from the sun. All true, all manageable in theory with enough engineering. But the thing that may actually end every colony attempt on Mars isn't on Mars at all. It's 3 planets away, roughly as big as 1,000 Earths combined, and it has been running the same operation for 4 billion years without stopping. And that's not even the part that most people realize. Jupiter doesn't throw rocks at Mars directly. It doesn't have to. It uses something far more patient than direct force. Here's how it works. The asteroid belt isn't a static pile of rubble sitting quietly in space. It's more like a conveyor belt, one that Jupiter quietly loads and Mars quietly receives. Jupiter's gravity doesn't grab individual asteroids and fling them toward the inner solar system. Instead, it does something subtler and, in the long run, far more dangerous. It creates zones inside the belt, invisible regions where the orbital rhythm of an asteroid starts to sync up with Jupiter's own orbit. Imagine you're pushing a child on a swing. If you push at the right moment every time, exactly once for every 3 or 4 swings, the child goes higher and higher without you pushing hard. You're pushing in rhythm with the motion. That's what Jupiter does to certain asteroids. The asteroid orbits the Sun, and Jupiter orbits farther out, and at certain specific distances from the Sun, their timing lines up again and again and again. Each time it lines up, Jupiter gives the asteroid a tiny gravitational nudge, always in the same direction, always at the same point in the orbit. Over thousands of years, those tiny nudges add up. The orbit stretches, it tilts. Eventually, it breaks loose from its original path and gets launched onto a new one, an elongated path that dips down into the inner solar system, past Mars, sometimes past Earth. What was a quietly orbiting rock in the belt becomes a projectile. Mars sits at the front of the line. This isn't rare, it isn't unusual. There are dozens of these rhythm zones spread across different distances in the belt, and any asteroid that drifts into one eventually gets launched. The belt doesn't empty out because collisions between asteroids keep knocking new material into those zones. The supply is essentially endless. The physics is continuous. And because Mars orbits closer to the belt than Earth does, it catches more of what falls inward. More than twice as many large asteroid approaches per year as Earth does. Mars faces roughly 52 significant asteroid encounters annually. Earth, for comparison, faces about 20. Mars gets the higher number and has no natural protection against any of them. On Earth, you don't notice most of this because the atmosphere does the work for you. Earth's air is thick enough, roughly the equivalent of 10 meters of water sitting above your head, that small and medium rocks burn up long before they reach the ground. You see the streak of light, maybe hear a distant boom, and that's it. The rock that would have been the size of a desk chair is now a shower of pebbles and hot gas. Mars's atmosphere is 100 times thinner. To put that in terms that mean something, standing at the bottom of a swimming pool, you have about 1.5 meters of water above you. On Mars, the atmosphere above you is about the same as standing in a room with almost no air in it, barely a whisper of pressure. An object entering Earth's atmosphere at full speed is braking against the equivalent of a wall. An object entering Mars's atmosphere is barely slowing at all. What burns up over a city on Earth hits the Martian surface close to the full speed it was traveling in space, faster than 50 rifle bullets stacked end to end, traveling together. At those speeds, the rock doesn't need to be large to be catastrophic. Something the size of a bus hitting at those speeds releases as much energy as the largest nuclear weapons ever built. Now picture your colony under that sky. The habitat module takes the hit first. Not a gentle pressure wave, an instantaneous transfer of all that speed into the structure. The outer wall fails in less than a millisecond. The pressure inside drops to near zero before any sensor can register the change. Your lungs, which were holding air at normal pressure, are now trying to hold air against a near vacuum outside. The air tears out of your chest. It isn't like having the wind knocked out of you, it's the reverse, your body trying to empty itself. Your eardrums rupture in the first second. The water in your mucous membrane starts to boil, not from heat, but from the lack of pressure, which lowers the boiling point of water to something close to body temperature. You feel a strange cold sensation across your tongue and nasal passages as the moisture there vaporizes. Your brain, starved of oxygen as the air rushes out, tries to compensate by racing your heart. Your heart rate doubles in the first few seconds, which burns through whatever oxygen remains in your bloodstream twice as fast. At the 30-second mark, your fine motor control is already gone. Your hands won't close properly. Your fingers won't grip. The emergency seal on the inner airlock requires 10 seconds of precise handwork. At 45 seconds, your vision narrows to a tunnel at the edges. By the time the tunnel closes completely, you have 8 seconds of useful consciousness left. Not enough to finish the seal. You are never going to finish the seal. The physics decided that before the rock was even visible from the surface. And here's the second failure that nobody in the colony briefing covers. After the impact, the ground itself becomes a problem. An impactor at those speeds transfers its energy downward through the surface rock in a wave, the same kind of wave that moves through Earth during an earthquake. On Earth, that wave passes through bedrock and loses energy quickly. Mars's crust in many locations is older and more fractured, the result of 4 billion years of exactly this kind of pounding. The wave propagates farther and lasts longer. Any structure within several kilometers that wasn't destroyed by the impact directly begins to vibrate. Pressurized structures are not designed to flex. They are designed to hold static load. Cyclic stress, repeated vibration, is different from static load, and it's what causes metal to crack and fail at welds, at seams, at stress points that tested fine in a controlled environment. A pressurized habitat that survived the initial impact may develop a crack in a weld joint 4 hours later, 6 hours later, a day later, as the residual vibration works through the structure. The leak is slow. The pressure drop is slow. The colony's air scrubbers work harder to compensate. The humidity drops. The temperature regulation system struggles. Nobody notices until the carbon dioxide concentration in the habitat rises past the point where it causes headaches. And by then, the engineers are already troubleshooting the wrong system, looking for a power fault rather than a structural breach. The point of no return in that scenario isn't the impact. It's the moment the carbon dioxide headache gets dismissed as fatigue. You're 8 hours past it before anyone runs the right diagnostic. The numbers make this permanent, not occasional. About 1/5 of all material knocked loose from the belt eventually becomes a rock that crosses Earth's or Mars's path. That's a ratio that doesn't change with technology, because Jupiter doesn't care about technology. The belt currently contains only about 4% of the Moon's total mass, a fraction left over after 4 billion years of exactly this process leaking material inward. That fraction has been enough to crater Mars more heavily than any other inner planet. The surface of Mars is a record of every impact the planet has absorbed, preserved in detail because there's no plate tectonics to resurface it and no rain to erode the craters away. Looking at Mars from orbit is looking at a document, a running count of what Jupiter's machine has delivered, written in rock, stretching back billions of years. The count doesn't stop. There's no final page. The obvious answer, and every person watching this has already thought of it, is to build the dome thick enough, strong enough, Put enough material between the colonists and the sky, and the physics stops mattering. It's the same logic that builds blast shelters and nuclear bunkers and armored vehicles. Enough material absorbs enough energy, and the people inside survive. The first part of that logic is exactly right. Material does absorb energy. Thicker is better than thinner. No argument there. Here's where it breaks. A nuclear bunker on Earth works because the atmosphere above it has already done most of the work. A nuclear blast travels through air. Air has mass. Air slows the shock wave. By the time the pressure wave reaches the bunker ceiling, it's already been attenuated, reduced by the kilometer of air it pushed through. The bunker deals with the remainder. On Mars, there is no remainder to deal with. The rock arrives at nearly full speed because the atmosphere provided almost no braking. The energy the bunker has to absorb on Mars is not the remainder after atmospheric braking, it's the total, all of it. An impactor that Earth's atmosphere would have burned to pebbles before it reached a bunker ceiling arrives at a Mars dome at full interplanetary speed. To absorb that energy, the dome material itself has to be thick enough to do what Earth's entire atmosphere normally does. That means meters and meters of material, not a dome, but a mountain, and a mountain made of engineered structural material, not rock. The mass required to build such a structure is not available on Mars, cannot be transported from Earth in any reasonable supply chain, and cannot be manufactured on-site without industrial infrastructure that doesn't exist. Every kilogram of protection you want to add to the dome's ceiling requires fuel to launch from Earth, propellant to land on Mars, and machinery to install. And the machinery requires fuel to transport the fuel. The problem multiplies faster than the protection grows. You don't build a thick enough dome on Mars. The math doesn't close. And even if it did, even if some future civilization could build a structure thick enough to stop a medium-sized impactor, the belt would eventually produce something larger. The protection that stops a desk-sized rock does not stop a house-sized rock. The protection that stops a house-sized rock does not stop a building-sized rock. Jupiter's machine runs without a size limit. The dome idea fails not because engineers aren't clever enough, but because the supply of threat has no ceiling, and the supply of building material does. December 24, 2021. NASA's InSight lander was sitting on the surface of Mars, 3 years into its mission, monitoring for seismic activity. At some point that day, a meteorite struck the Martian surface close enough for InSight's instruments to detect it, a magnitude 4 Marsquake, which is roughly the kind of ground shaking that rattles dishes in kitchen cabinets on Earth. The seismometer recorded the event. The cameras captured fresh impact craters nearby. Scientists confirmed what InSight measured. A rock that Earth's atmosphere would have burned to nothing had hit the Martian surface at high speed, transferring enough energy to shake the ground across a measurable distance. Nobody was there. The habitat was empty, because there was no habitat. The moment was data, not disaster. But the data was specific: impact location, energy transfer, ground vibration radius, time of day on the Martian calendar. Everything a colony planner would need to model the threat and realize what InSight had just measured was not exceptional. It was Tuesday. It was routine. Mars records events like this as part of its normal year, the way Earth records rainstorms, not as emergencies but as weather. Not rare, but expected. Not survivable with a thin-walled dome and a good attitude, but survivable maybe, only if you are under the ground when it happens. The realistic answer is underground. Not domes, tunnels, lava tubes, long hollow spaces left over from ancient volcanic activity already exist on Mars, some wide enough to fit a city inside, their ceilings made of meters of native rock that has been absorbing impacts for billions of years and is still there. Underground, the impactor problem largely disappears. Rock attenuates the energy the same way Earth's atmosphere does, by having mass that the shockwave has to push through before it reaches you. A lava tube ceiling several meters thick is more protection than any dome you could build and ship from Earth. The physics actually works underground. But underground is not the civilization in the colonization pitch decks. Underground is no windows, no horizon, no fields of red dust under a pale sky. Underground is tunnels and artificial light, and the knowledge that the world above you is not your friend and never will be. Underground means every supply drop from Earth has to be received at a surface landing pad and then moved below ground, which means airlocks, transfer vehicles, exposure windows, risk every time something new arrives. Underground means any emergency that forces someone to the surface, equipment repair, antenna maintenance, a rescue, is an exposure event planned around impact probability windows rather than convenience. Underground means the colonization story humanity told itself for 100 years, the gleaming dome against the rust sky image, was never actually possible. It was a story about a planet without Jupiter. Mars has Jupiter. Jupiter didn't just stop a planet from forming 4 billion years ago. It created an ongoing process, a machine that runs without supervision, requires no maintenance, and never runs out of ammunition. Mars is not a frontier waiting to be settled. Mars is a position directly downrange from a billion-year-old system that has been doing exactly what it does right now, continuously, without ever receiving the instruction to stop. The dome was a beautiful idea. The physics engraved on the wall was always legible. We just preferred not to read it.